All right. First order of business for us is exam stuff. So we have an exam scheduled for tomorrow, and it's going to be Chapter 6, DOE 1, DOE 2, and that'll be it. Jeff. What's that? Did you miss? No, that's a 2. It's a creative 2. Sorry. Okay. So like the exam before, you have an equation sheet that you can write equations. I don't want any words. I don't want any explanations on the equation sheet. No worked out examples, just equations. A couple other things schedule-wise. We have ABET visit coming up next week. So Monday, I probably will have to cancel class because I've got a meeting. This is sorrow expression. This little, the opposite of Augustine's expression there. So Monday, we probably won't have class. I'll let you know. Exam also, we have it scheduled for tomorrow. It doesn't matter too much to me if we push it back a week till the next Tuesday, if that works. No. So it's tomorrow. Tomorrow. Okay, good. All right. So it is tomorrow as scheduled. Okay, I understand the feeling. So. The old exams are on Blackboard. Last couple years, I generally make it to DOE 3, and we just didn't quite make it there this time, but it was close. So you see a lot of the old exams have center points and maybe blocking on those exams, but we're not going to have that on this exam. Otherwise, homework. Are all the homework solutions up? Not up? I will. As of yesterday, okay. I'll ask the grader to do that. Please remind me right after. Send me an email right away so I can get that to the grader in case I forget. Please, Augustine. Oh, okay. Questions about the exam? Work the homework. Group problems in class, old exams. There should be a lot of material for you to study. Make sure, we had a lot of homework in Excel and Minitab. Make sure if you're starting with a data, that you would start with in Excel, make sure that you can do everything by hand. That's the big difference. If you've been typing the formulas into Excel, you ought to be able to know what they are. So you'll have to do things by hand on the exam. You're not going to have Excel available to you. As far as sig figs go, we have our sig fig convention, but on the exam, I'm not really concerned about you implementing it. I would ask, why don't you just give me like 4 digits for every number on the exam? That way it's quite a bit easier to figure out where you pulled t-values and that kind of stuff. If you're bring your book for the tables. If you have an electronic book, I send out the tables for the last exam. Just bring those tables, and make sure that I can tell if you're going to get a t-value or z-value from a table. Make it very clear where you got that from. Don't just put the number down and make me guess what your area was and your degrees of freedom. Just write them down. Okay. All right. That's pretty much the basics on the exam. So we'll have it tomorrow, and we'll start right away at 2:25 and end at 3:40. It's 5 problems. First one's fairly short, kind of a short answer, a couple of parts. And then 5 problems, a mix from the DOE stuff and the Chapter 6 stuff. Make sure you can do all the steps in the hypothesis tests. So anytime I ask you to do something with Chapter 6 stuff, I want you to have every step in the hypothesis testing procedure on there. Okay. Here's where we left off last time. The last topic, I believe, in this DOE 3 set of notes is blocking. And what we're doing in blocking is we're trying to figure out, these are sources of error in our experiment. We're not really interested in studying them, but we just want to remove them from our experiment. We want to block out their impact on our results because they're just adding noise to the experimental campaign. So we talked about blocking in general last time. And it's always good to go through a couple examples, especially in this case. So as an example of blocking, let's say we're doing the example that we're always doing, which is some chemical reaction. And we've got 2 factors, temperature and time, and we're measuring something about the reaction. Seems like we always have yield. There are other things like selectivity, which is related to yield or reaction rate. There's other measurements, but all these examples seem to have yield. So we're measuring the response, and we have a replicated 2 squared design, so k equals 2 factors. So it's replicated. We have 8 runs. They take a bit of time, so we run them over 2 days. And notice how they are just sort of randomly picked, which experiments occur on day 1 and day 2. And if you look at, box plots of, this is just an example. So these are getting at x1, x2 settings. And you say, okay, if I'm going to think about the x1 effect, here x1 went from low to high, where x2 is constant, and same thing here. Right? If we average those 2 effects, or those 2 estimates of the effect, we would look at x1 and say, it's probably not doing anything. When we look at the box plot, we've got a whole lot of noise here, right? And these effects are fairly small compared to the noise. Just nothing real high level here, just looking at, boy, that's probably not going to show anything as significant. So then the idea is, well, what if, when we're trying to figure out why do we have so much noise in our data, someone had the suggestion of, well, the equipment seems to be a little bit finicky. On one day we can get the results. On another day we can try to replicate it and get very different results. So what if we think just the day we run the experiment is a cause of variation? So all the things that go into kind of setting up for one day and then setting up for another day cause a lot of variation. Someone thought maybe this is the case. So let's redo this, but now in this case, let's try to block out the impact of this day-to-day variation on our experiment. So in 8 runs, we could run a full factorial on day 1, right? 4 runs, and we could run another full factorial or repeat the full factorial on day 2, right? So let's say we do that. So here we have day 1, we have a full factorial in those factors, and in day 2, we have a full factorial there. And so now, just as an example, let's say we get results like this, and we see, well, now when we look at, what is the x1 effect, it would be that plus that and that plus that. And now we've got pretty much all those slopes, if you will, look the same. So in this case, if we what we call block on days, we probably will see a lot of significance in our factors. And we notice that suspicions that we had that a big source of variation is just what day do you run the experiment on, right? So notice on day 2, everything just shifted down, right? So each data point shifted down. It shifted down about the same amount. So if that really happened, this is all made up stuff, but if that really happened, we would say that was good for us to block out the day-to-day variation. Does everyone get that? So see how, now this is analogous to what we talked about before when we had the different cars and their variation. We're just trying to block it out. It would just sort of shift our results around, and we just wanted to remove that. So somehow there is this shift because of this, what day we run it on, and we'd like to remove it from our experiment, and we can do that with this design. But we need to get a few more details in order to finish it off. So how would you estimate, well, the block effect would be that shift right there, right? Probably be the average of these guys minus the average of those guys would be that, would give us, we'll call it a block effect. And keep in mind, it's just, the block is, it's shifting all of our data up or down. Okay, so, but now when we look at this, right, if we treat this block just like any other factor, right? If we treat it just like the other two factors, we would say we have a 2 to the 3rd design, which would be 8 runs, and we have no degrees of freedom to estimate noise. Does everyone see that? Everyone buy that? So that's what we need to figure out now. How do we estimate the noise? Before, how many degrees of freedom did we have here? We had a replicated 2 to the squared design. Let's see, 1 right answer. Anyone else? How many degrees of freedom? Good. 4 degrees of freedom. Right? 1 at each corner point. So now, when we add a blocking variable, you'd think, well, if we're only adding one thing, if we're only calculating one blocking variable, that'll use up a degree of freedom. Seems like we ought to have 3 degrees of freedom left, right? Before we had 4, and we added one more thing. We're calculating this block effect. Seems like we should be able to get 3 degrees of freedom out of this. Okay, so let's look at this. How do we get there? We make an assumption, if you will. Now, and it goes back to the nature of what a blocking variable is. So this is a good example when we're talking about the day you run an experiment on. Okay, a blocking variable isn't something that you can, typically when you make something a blocking variable, it's not something that you can readily control and use to optimize something. It's something you don't really have a lot of control over. It comes in and it messes stuff up, okay? So because of that, so if you think of the day-to-day stuff as stuff we can't control, then if we think about our factors, temperature and time, if they're going to be significant, then their effect has to be quite a bit bigger than the effect that that they interact with the block effect. It's kind of a big whole lot said right there. So think about this. The temperature effect. Right? For the temperature effect to be real and useful to us, it should be doing something on day 1, and it should be doing about the same thing on day 2. Does everyone buy that? Just practically speaking. If there's an interaction between temperature and days, that would be weird. If days is truly a blocking variable, and we say, well, on day 1, temperature had this really big effect. On day 2, it really didn't have a big effect. Then we can't really use temperature to do anything. Does everyone buy that? Right? The temperature wouldn't be a real factor that we would hang our hat on because we can't predict if it's going to have an effect or not if there's this interaction between that factor and the blocking variable. Same with time. If time interacts with the blocking variable, so the reaction time, well, it depends on what day you have. It does one thing on one day, another thing on another day, then it's not a really reliable factor. So that we're coming at it from a very practical viewpoint. So because of that, if our experiment is going to mean anything to us, we would have to say that our factor effects have to be a lot bigger than the interactions between the factors and the blocks. So that is going to be our assumption. If that's not the case, then we can't really rely on those factor effects to optimize whatever it is we're trying to optimize. And so that gets at the nature of what a blocking variable is. Generally, something we can't really control, or we're not interested in controlling. It's too hard to control, those sorts of things. So another way to say this is that if the factor effects have to be a lot bigger than how the factors interact with the blocking variable, then we could use those factor block variables to estimate the noise. Right? All along in DOE2, we were saying the effects have to be much, much bigger than the noise. So we were comparing those two things. So for us in a block design, we can take these block interactions, or these factor block interactions, use those to get the noise, and then compare that with the factor effects. Yeah?
Is there a way that we can confirm that the interactions
Pardon?
Is there a way we can confirm that interactions don't do anything?
Is there a way that we can't really confirm that. We could look at their relative size, but again, it's a very practical way we're coming at it, that if those factor effects are, big, all that means, if these block interactions are big, what that really means is they're big compared to the factor effects, and we could also just say, well, that means the factor effects are too small. And that just means we don't really have anything we can hang our hat on to control this process. And practically what that would mean is we need to do some work to reduce the noise if we have a chance, or start looking for some other factors, because what we thought was going to pan out didn't. Okay, so let's think about this. We'll talk about this. So we're going to use that to estimate the noise. How do we do it? We'll show that in an example. We probably need to, but we're going to calculate the blocking factor interactions, and then we're going to use those to get SE directly. Now, block interactions, here's, that's shorthand for the interaction between a blocking variable and a factor. Remember, factor is what we're trying to study. A blocking variable, we're just trying to get rid of it. Any questions so far? Okay, so let's look at an example to see how we would analyze. It's how we're going to use this assumption. That's the really new thing here. Okay, so we have a chemist doing experiments in the lab, and two factors: temperature, amount of catalyst, high-low values for each, and pH, sorry. And we have pH, high and low values for each. So we have three factors. For a full factorial, we need 8 runs. And again, when they were doing this experiment, there we have 8 runs. And we said, all right, let's do it on week 1, do it on week 2. And it's fairly common that things can vary with time. Right? Lots of things change with time. So days or weeks or some time element is a fairly common way to block an experiment. But it's not the only way. It could be, on this set, this guy ran it, this person over here ran it on a different day. You can block on lots of factors. Just a lot of our examples end up being days or weeks times. So just mentioning. Okay, so what we have is they're worried that things may have changed between week 1 and week 2. So let's try to block out that source of variation. And how do we do it? Well, here we have, if we ignore that, if we ignore the potential impact of week 1 and week 2 of shifting all of our results, then right now we have a replicated 2 to the 3rd design. We would have how many degrees of freedom? How many degrees? So when we calculate a T star, if I call week 1 and week 2 just replicates and I ignore any change in week 1 and week 2, how many degrees of freedom do we have? 8. Good. All right. So now, instead of that, then we're going to add this blocking variable of weeks, which would mean we have a full factorial here, and then we have this other full factorial in week 2. So we're going to add this blocking variable to the design. So we went from a 2 to 3 replicated. We're going to add the blocking variable to our computation table. So that's what we have. That's what this looks like. So x1, x2, x3 were temperature, catalyst, pH. So this was our factors: temperature, catalyst, pH. And then this blocking variable would be, the low level corresponds to week 1, and the high level corresponds to week 2. So all these yields, where are you now? Right here. So notice all of these correspond to that week 1. Does everyone see that? Sorry, it's so small. And then the next ones correspond to week 2. So that's how we set up our analysis. Then we make the full computation table of a 2 to the 4th design, and it looks like we've burned up all our degrees of freedom in doing so. So we have 16 experiments, and in this 2 to the 4th design, we have 15 effects and a mean. We've calculated 16 things. We're out of degrees of freedom. So that's where we're going to employ our assumption that the blocking interactions really only tell us something about noise. So we look at these and say, which of these columns represent block interactions? So anytime you have a factor that interacts with x4, which is our blocking variable, that would be the blocking interaction of factor 1 and the block, which is x4. Does everyone get that? Right there, there's a blocking interaction. Anything with a 4 in it, in this example, all these guys. So we've identified the block interactions. These are in red here. And so we can calculate their effects. And we assume that those effects are just due to noise, right? So I have 7 numbers. I could calculate the standard deviation of 7 numbers, which gives me this value here. There's a detail I'll hit in a little bit. But just think, we have 7 factors, and we say those factors are just noise. If I calculate the standard deviation, that quantifies the noise, right? But a couple distinctions. First thing is, these numbers are effects, right? They're not individual data points. This is the first important thing. These 7 numbers are effects, so when we calculate a standard deviation from them, it is SE that we get. Right? These numbers tell us how the effects are bouncing around. So we get SE directly from it. Is everyone okay with that? Okay, so this assumption we get SE directly, and how do we calculate that effect? So our standard deviation is each data point minus the mean squared, add them all up, divide by the degrees of freedom. And this is what I did. Notice a couple things. I left off the 0. So when we assumed that these were noise, this is the one detail. When I did that, I made an assumption that the mean of those effects was 0. I said, I know the mean, and it's 0. So that means I left off the 0, the minus 3, minus 0 squared, minus 0.3, you know. I left off the 0 there. In a block design, yes. This assumption is only germane to blocking designs, and we will always make it. Okay, now the other thing is, I divided by 7 and not 6. So this is probably the other thing that you got to pay attention to, is remember we had a couple, we've run into a couple formulae for standard deviation, right? We had, the one we're used to using was xi minus x bar over n minus 1, right? That's the one we're used to using. But in this case, and the n minus 1 came about because we said, oh, we burned up a degree of freedom when we calculated the average. In this case, instead of calculating the average, we're going to say we know it, it's 0. And in that case, we don't burn up a degree of freedom in calculating an average of these. We assume it to be 0. And so in that case, we say we know mu. And this was another formula that we saw, although briefly, for standard deviation. And when you look into Excel, it had the standard deviation .s and .p. Remember that? Does everyone see that? Right? This is the one for p, meaning population, which means you know the population mean. And if you know it, you don't have to burn up a degree of freedom to get an x bar, so you divide by n instead of n minus 1. And so in our case, we're just assuming that. We're assuming the mean. We say we know it by assumption it's 0. And that's why we have 7 instead of 6 here. It's a detail, but it's fairly important in order to get this right. So then we get SE squared, we get SE, and then we proceed as we have done before. Once you have SE, then T is just the effect divided by SE, and it gives you T statistics. Our hurdle value, I have 0.95, it should be really 0.025 alpha over 2 is how we've been writing it. So we have 7 degrees of freedom. Again, that makes sense too, because we started with 8, and we only wanted to burn up 1 degree of freedom to calculate the block effect, which should leave 7. And by this assumption, that's indeed what we have, 7 degrees of freedom. So now we can look through here, and as per usual, we say, hey, these things are significant. Oh, look, here's something neat. The block effect is really, really small. Which may tell us that, oh, you were worried that there was a difference between week 1 and week 2, but the data don't seem to support that. We probably could have treated this as a replicated 2 to the 3 design and not worried about blocking on weeks. So sometimes you'll see people when that happens, sometimes they'll say, oh, okay, the block effect was small. That means it's not doing anything. I'll just get rid of it, and I'll reanalyze this by ignoring that blocking variable. I'll reanalyze it just like this with a replicated 2 to the 3rd design. But that's fine. That's fairly commonly done. But doing that, you only gain 1 more degree of freedom. You don't change any effects. So doing that is probably not going to change your results too much. So that's what I'm getting at here. I think general practice is when you have an insignificant block effect, you remove it and reanalyze it, but you generally don't see a lot of difference. We'll get into this question a little bit. The thing that changes, the only thing that's going to change when we do this is SE. The factors won't change. Right? So this, the effects, I should say, that number there is not going to change. None of those things are going to change when we do this. So we'll start thinking about that in the group problem that we're going to hit in a little bit. Any questions about blocking designs? So this was an example where we had two levels of this blocking variable, right? We had week 1 and week 2, but you're not limited to that. You could have week 1, week 2, week 3, week 4. You could have several levels that you want to block on, and how do we handle that? So it's pretty easy when we have a blocking variable that has two levels. If you have more than two, it can be a little bit trickier. So I think that's the next example we have here. So here we have the same, it's a different design, but the same sort of situation. We have three factors, and now we have, well, we say we have 4 blocks. We have a full factorial, so many days after incubation, a full factorial a little bit later. We come back later and measure it again and again. And so what we're wondering is, let's treat these as a block. We might see shifts in the results in each of these time periods. So now, how do we handle this in our setup? So we have 4 blocks. And how are we going to squeeze that into our computation table? Well, before we had week 1, week 2, or day 1, day 2. We had really 2 blocks. So when we had one blocking variable, and it had 2 levels, and that handled the 2 blocks. But if we have 4 blocks, then we could introduce 2 blocking variables. They're just simply placeholder or dummy variables. So we can introduce an x4 and an x5, and we could keep track. When they're both minus, say that's this block. When they're this way, that's this block, and so forth. Change colors. So if we have 2 variables, there's 4 possible high and low combinations of those 2 dummy variables, and they'll correspond to our 4 levels. So that's what we do. We would add an x4 and an x5. We'd make the full computation table. We'd get blocking interactions, assume they'll be equal to 0, and we'll get the noise that way. So let's look at that. It looks like a bit of a mess. So that's our 3 factors. And here's x1, block 1. I'm trying to draw these straight. It's very difficult. So there we have the first factorial of 8 runs, the next one, the next one, and the next one, and they correspond to, when both the dummy variables, these are the blocking variables, when they correspond to something different, we've got the next week. Does everyone get how we set that up? And so each one of these is one of these. We make the full computation table. It's a bit of a chore when you have 2 to the 5th, you have 32 runs. And we identify each time Remember, these BIs are interactions between factors and blocks and blocking variables, I should say. So notice this thing. Every time we have a D or an E, we'll call that a blocking interaction, except be careful there. That's not a blocking. D and E are there are two blocking variables, so that's not a factor in a blocking variable interaction, right? It's interaction between the two dummy blocking variables. And so what that ends up being is we end up having three block effects that we can calculate. If we have 4 levels, we have 3 spaces or jumps between the 4. So those are the estimates of the blocking effect. Whoops, circle the wrong one right there. So those are blocks. And all the other BIs are the blocking interactions, and they're in red. They're in red here, and so what we're going to do is take each of these effect values. So here, to get SE, I took -1 minus 0 squared plus 0 minus 0 squared plus 4 minus 0 squared, on, and divided by 21. Instead of that 15 that was running. And that's how I got SE. Did I show SE in the notes? Oh, there it is. It's 4. Okay, so there's just a few details that we have to just be aware of when we do this blocking designs. Is that okay? This is not a blocking interaction. It's block and block effect when you have more than one blocking variable, and we have to divide by the total number of degrees of freedom correctly. So it's n and not n minus 1. And the other thing is we get SE directly out of this, not SP. We get the noise of the effects, because these are effects that we're quantifying how they are varying, how they're bouncing around. Okay, so then these are the results on Minitab. Let's get to this group problem. It's also good review for the exam because we're trying to do our regular analysis. The idea on this first one is treat this as a replicated 2 to this 2 design. So here are the yields. And let's analyze this. If we didn't assume that this blocking variable had an effect and we treated them like replicates, what do we get? Any questions? Talk to people around you. Question? All right. Oh, so treat these as replicates. So the variance is that minus that squared plus that minus that squared divided by 2 minus 1 is 1. So you got, is that an 8?
Yes.
Good. 8, 2, 8, 2. Yeah.
But for SP squared, so you like multiply these to the degree of
Mm-hmm.
freedom, and then you divide by.
Then you and add them all up. Yep.
Yep.
So 20 divided by the total degrees of freedom. Yep. Question, Danica? Got it? Okay. Anyone getting those numbers for noise? Yes. So that should be second nature by now. Questions?
And that is the total number of rows.
Yes. Yeah, it's kind of a squiggly one. That's a better one. You don't get a T star. How many degrees of freedom total? 4. So 2.776 is our hurdle value for T. And you could calculate T values for each effect, but I ask you to do it this way because it will speed you up on the exam. So we could take our hurdle value for T star, and get it to a hurdle value for effect, and then we only have to do one calculation and figure out we've got what thing's significant. Is temperature significant? Yes. 10 is bigger than that. Time? Yes. The temperature-time interaction? No. Okay, good. That is our standard analysis. That's not blocking. That would be an easy problem on the exam. Right? Right. Good. Now, we're going to say, let's take these same data and now treat the blocking variables that sometimes we say blocked on replicates, that we had the first block and the second block, and we add the blocking variable there. And we'll analyze that come Wednesday. All right, good luck on the exam. If those people that need to take the exam somewhere else, I've got to see those purple sheets.